This is working? Okay. Thank you, Silka. Thanks, everybody, for sticking around. Yeah, Silka's right. There's not a 2 missing in my presentation, although we do only, up till now, develop CO2 lasers. This new laser technology, I have to say, though, is some of the most interesting technologies I've worked with in my 25 years with lasers. But in fact, it's actually not new. You see the picture there. Carbon monoxide lasers were actually developed in the 60s and 70s. They were actually invented by Kumar Patel in '65, the same time he invented the CO2 laser. And so those carbon monoxide lasers have been around for a long time. There's lots of reasons why they want to develop the lasers, lots of advantages of CO over CO2 lasers. The problem is they never got them to work. They never got them to work for more than 10 hours. So there are a lot of difficult tricks with CO to make it work. One of the things they had to do back in the 60s, and by the way, I'm telling you all this because we did get it to work, obviously. The trouble they had in the 60s and 70s and even the 80s was they could get tremendous amount of power out of these lasers, but they didn't last more than, say, 10 hours. But they could get multi-kilowatts out there. They're ultimately the most efficient laser there is. It's a cascade laser, and I'll show you a little bit about that later. But what would happen is carbon monoxide would do strange things. And really, these lasers are all about the gas dynamics. So carbon monoxide can dissociate in the discharge into carbon and oxygen, and that carbon is black. And it blackens the inside of the laser, and you know what happens next, right? The laser dies. Another thing that happened way back in the day is in order to get efficiencies out of these lasers, they needed to cryogenically cool them. So they would cool the laser down extremely cold. Then what could happen is carbon monoxide could find another oxygen, turn it into carbon dioxide. Now you got a carbon dioxide laser that's running at cryogenic temperatures, which turns the whole thing into a big box of dry ice. And so after 10 hours, these things were filled with dry ice. So it was a difficult development. Ultimately, CO2 won the day, has been the workhorse for many, many, many years, and CO has been used maybe at very, very low powers, milliwatt level in different scientific aspects. But today we've been able to develop it into an industrial laser. And I want to talk a little bit, actually the slides are a little bit screwed up, but I want to talk a little bit about the differences between a CO2 and a CO laser from the inside. And I want to say right away, the really fun and interesting thing about this product for Coherent is that fundamentally the hardware for a CO2 and a CO laser are the same. The real difference is in the gas dynamics. And I say that really the difficult challenge, even CO2 and CO lasers, is actually controlling what I call this symphony of chemical activity. So we have fully sealed CO2 lasers and now fully sealed CO lasers. And inside, for example, a CO2 laser, you have a bunch of different gases, mostly nitrogen, helium, and carbon dioxide, of course. And then there's 5 or 6 secret gases that everybody puts in there to make things do different things. But those are sealed up, and those gases have to live together for tens of years. And they have to react properly with each other to keep the mixture the same. And then they have to also react and behave with the other materials, the metals and the non-metals that are part of the construction of the laser, and any contaminants in there. So all of that has to be engineered. All of that has to be properly manufactured in order for these lasers to last as long as they can. And we've learned a lot with CO2 lasers that we've applied to CO. And that's part of the reason we've been able to make these CO lasers. The other part is that we stumbled on the secret solution, right? We figured out how to make them last. But I think even if we had that solution 20 years ago, we wouldn't make them last because we wouldn't have had all the other things in place. So just real quick, how a CO2 laser works, because I want to compare it to a CO, and then I am going to talk about applications, don't worry. CO2 laser really consists of nitrogen, CO2, and helium as the major components. And the nitrogen gets excited in the discharge, as you see here, and it transfers its energy, vibrational energy, to the CO2 molecule. So now this is sitting in an excited state, and it can do 2 things. It can radiatively decay, giving off a photon down to another one vibrational state, a lower vibrational state, and give you a 10.6 micron photon, or it can go down and give a 9.6 micron photon. Okay? From there, the helium comes in, and the helium collides with the CO2 molecule that's now in this vibrationally excited state, and non-radially drives it back down to the ground state. So now this CO2 molecule can go back, get re-excited, and start the whole process again, and make the laser. CO is very different, and this is what's kind of cool, because all these lasers look the same. They look like CO2 lasers, but inside a CO laser, now you have a ladder of vibrational energy levels, because it's a diatomic. Okay, each of these has a little bit different spacing because it's anharmonic. But what happens in the same, using the same exact RF power supply, you now excite these CO molecules up into different higher vibrational states, okay, up to say V equals 5. From V equals 5 up, they start colliding with each other, pushing themselves higher and higher into the vibrational ladder. So now you have all these CO molecules excited in these states. And what's really exciting about a cascade laser, and different than a 3-level laser like in a CO2, is that now you have a molecule in an excited state, CO in an excited state. It transitions to the lower state, giving you 1 photon. And then in this case, the photon is at 5 microns. But now that ground state becomes the excited state for the next transition, which becomes the excited state for the next transition. Becomes the excited state for that. So now you have 1 CO molecule that's able to kick off a lot of photons in this cascade effect. And so you have a really highly efficient laser. Again, very different than the CO2, but the gas dynamics and how you control the gas dynamics are very similar, and the experience you need. So now you have this ladder, and you're kicking off all these different photons at around 5.5 microns. What does the output spectrum look like? Well, the output spectrum, because again it's an anharmonic system, is quite broad compared to the CO2. So the whole width of the output is about 0.5 microns wide. And within that 0.5 micron envelope, you have all these different transitions here. You know what, actually, this aspect ratio is cutting off a bunch of bullets, so you guys are just gonna have to trust me. I don't know if you can change it or not. It's cutting off, is there a way of doing that? It's cutting off half of my lines. I don't know if this guy can do it real quick. I can talk while you're doing it. I kind of remember it. The cascade laser runs on a bunch of different multiple lines, about 40 different lines here, 30 or 40 different lines, and that has a number of advantages. One advantage is it's extremely stable. So typical CO2 laser has a power stability, you can let it run off the screen if that's a power stability of roughly plus or minus 5%, 5 or 6%. A CO laser is at 0.5% stability. Again, running off all these lines. Another really cool and interesting advantage of having all these lines running is the laser is 100% immune to back reflections, okay? Because any one of these lines won't be in phase at the same time with the resonator. And so, yeah. And so what we've been able to do is stick a mirror right in front of the laser, send the entire reflection back. That's fine, like the entire reflection back, and it doesn't disturb or destroy the laser. So what do we have to offer? I mean, as I mentioned before, the hardware between CO2 and CO lasers are very similar. And so really you can take any of the CO2 models that we have today and turn them into a CO laser. So right now we have the potential to deliver CO lasers at 5 microns from 30 watts up to 1 kilowatt. And here are some examples of some of the output powers that we typically get out of our CO2 lasers compared to our CO lasers. And you see that roughly you get about 70% of the power at 5 microns that you would compared to 10.6, right? So for example, our GEM 100 laser typically puts out about 130 watts at 10.6 microns. At 5 microns, it puts out about 90 watts, okay? So that's one of the exciting parts. We're actually able to expand our entire product line. We're also able to get high peak powers. So we have a via drilling laser that we call the E400 IXX. It's capable of peak powers greater than 2.5 kilowatts. We can get the same type of peak power out of the CO laser. So, okay, what does this matter for applications? Because that's what we're all here for, right? Oh, there we go. For applications, there are 2 real advantages of the CO laser at 5 microns. One, I'll call it light material interaction advantage. So 5 microns is not 10 microns, and it's not 1 micron. So we're really in a new regime here at 5 microns. There are no lasers, no commercially viable lasers that can produce hundreds of watts at 5 microns, okay? The only one that can produce more than 100 watts or so is a free electron laser, which is not commercially viable for most people. And so the advantages of 5 microns are the different absorption of material. And I'll show you some examples how the lower absorption at 5 microns compared to 10 microns in glass is really important. All of us know that typically higher absorption is important is in materials processing. And again, compared to 10 microns, CO2, there's higher absorption in metal, steels, metal oxides, ceramics, certain films and plastics, and even human tissue. So there's a lot of potential there. Then there's lower attenuation in AOMs, which are often used in front of CO2 lasers. In fact, the attenuation is 4x less. And there's an interesting article dating back to '88 that has a bunch of different very interesting applications that were done on, again, one of these big lasers that lasted 10 or 12 hours. Another really interesting potential for 5 microns is the potential to fiber couple it. Okay, so the holy grail for CO2 has always been to fiber couple it, right? And it's been the Achilles heel against the fiber lasers in the past. And the reason is that there's so much absorption in most of the materials. Chalcogenide glass is one material that people have made fibers out of that has very, very, very low absorption in 5 micron range. And so there's real potential to be able to fiber couple this CO laser. The other advantage in applications is just the optical advantage, the numbers, the geometry, and the fact that the laser, it's at 5 microns. So 5 microns is half of 10 microns. So the wavelength is half of that of the CO2. And that means you can get down to much, much smaller spot size. So the diffraction limit for a CO2 laser is roughly 55 microns. The diffraction limit for a CO laser is 25 microns. So imagine hole drilling or the kerf widths are a lot smaller. The other advantage of having half the wavelength, which can give you half the spot size, is you get 4 times the fluence. So you can put 4 times the power density down onto your material. And I'll show you one example of where that's actually driven an application. So you can either use lower power lasers, less expensive laser. You can also reduce heat affected zones by not having to put so much power into an application. The other thing is if you take the CO laser at 5 microns compared to the CO2 laser and you keep the spot sizes the same, okay, the 5 micron laser, a CO laser, will have twice the depth of focus, right, which will give you twice the scanning range or open up your process windows in many cases. So now we want to talk about a few examples. The first example, which has been really popular at this conference, is glass cutting. So I don't need to tell you guys how to cut glass by far. We're going to talk about how to cut glass with CO. Typically, you need to create tensile stress induced by laser quenching process when you're cutting with CO2. And what that means is you basically take a laser, you heat the glass up, and then you follow it by, here's a laser, you follow it by a cooling jet, okay? And that creates a scribe or a vent in the glass, in thicker glass, for example, anything above half a millimeter. And then later you mechanically break that glass, okay? What's very important is not to add too much heat into the glass, okay? And that's always been a problem with CO2 because it's kind of non-intuitive, but if you look at this transmission spectrum, CO2, and these lines here all represent CO2 transitions, are 100% absorbed by the glass. So when you put CO2 light down on a glass, you get penetration between 3 and 8 microns. Everything is absorbed by the surface, okay? Extremely strong absorption. And so what typically people do when they're cutting glass with CO2 is they'll elongate the beam. They'll stretch the beam out along the cutting path in order to stretch the heat out, basically, distribute the heat. And then the heat, which is used in the process of this stress cracking, if you will, or stress vent generating, that heat is deposited into the bulk of the glass via diffusion. So you can see from this graph that it takes some time for the light to diffuse, or the heat to diffuse from the surface down into the glass where it needs to be, okay? And then that elongated CO2 beam is followed by a cooling jet, and that cooling jet creates the vent, the stress that's needed to create the vent. The problem with this process is, again, the heat or the laser light is generated so strongly on the surface that you can end up having residual stress in the glass. When you create these vents, you want transitional stress to create the vent, and once it's created, you want no residual stress at all. And you can see from these pictures, the different shades here indicate differing levels of residual stress that have been left in the glass, and most of that is due to this heat damage. And when you have that residual stress in the glass strength is significantly reduced. These are basically defects in the glass, okay? The beauty of the CO laser is, now you can look at the spectrum again, sorry it's a little smaller, but now you see that at 5 micron, the glass doesn't absorb 100%. So the light at 5 micron actually penetrates deep into the glass. So it's actually deposited into the glass rather than being absorbed 100% on the surface the way it is for CO2, okay? And what that allows you to do, that allows you to control the amount of heat in here. So in fact, this, depending on the glass, the penetration is anywhere between 50 and 80 to 100 microns deep into the glass without diffusion. So now you're processing at the speed of light, basically. Now your scan speed, the control over this line, all of this becomes less important. And so these are some pictures of, this is Corning, what everyone's calling Gorilla Glass. This is a very strong glass. The depth of layer is 35 to 40 microns. We're able to cut this at 250 or so millimeters per second with 80 watts. So this is not a real expensive laser, by the way, too. And you can see that it's perfectly clean, defect-free. And the strength, glass strength, with the 4-point bend tests we've done are all greater than 850 megapascals. So it's still very, very strong glass. So that's one example of where CO lasers, where there is an advantage to not absorbing so strongly. So again, with glass cutting, as you can see, since the 5 micron light from the CO laser isn't as strongly absorbed here, we don't necessarily have to create a line the way we do with CO2. This represents the line that's created by CO2, and then there's the cooling jet behind that. Because the CO laser deposits the light depositing directly into the bulk, we can change that line into a circle. And now that circle can do radial cuts. And so you see here, these are some radial cuts that we did on fairly thin glass, in fact, that are through cuts in this case. So basically you're taking a circular saw and turning it into a jigsaw in this case. So big advantage of not having super high absorption. Here's another example of glass cutting that's very difficult by any other means, mechanical or laser, thin glass cutting. So this is 50 micron thick. It's Corning's Willow glass. What I'm showing here is the edge of the glass. And so I have a little cartoon here. This is the edge of the glass. This white part is the edge of the glass, and the yellow is the outside. So this white part you can see. This is the way the glass was delivered to us. We don't know how it was cut. It was either cut mechanically with a diamond wheel, or it was cut with a CO2 laser or a picosecond laser. I have no idea. All we know is that whatever they used for the cutting process created a lot of defects in here, okay? Below is a piece that we cut with the CO laser, okay? We used 29 watts, focused circular beam, no cooling jet was necessary, and we have a perfectly clean edge in this case. And what a perfectly clean edge does in thin glass, this isn't strengthened, it's thin glass, it gives you the strength. There are no defects. So this particular piece, we would pick up and bend slightly and it would crack. And the cracks, of course, all start at these defects, okay? The piece that was cut on both sides with the CO laser, you could wrap several times around your finger. Okay, so having this defect-free, and this, you can see there's another picture of it, what they call water glass finish. There are no defects when you cut with a CO or typically with a CO2 laser. So the defects are immeasurable in that case. Very strong. Another thing we can do with the CO laser, again, because of the 5 micron wavelength and the penetration, the absorption or lack of absorption in glass, is we can drill holes, very stable holes. And drilling holes in glass is interesting. One application, of course, is glass interposers for chips. Another application listed here are what are called light guide panels. And light guide panels are basically diffusers that are on most displays, most flat panel displays, and including the large TVs, all have diffusers. And today they're made out of acrylic, and the acrylic is fairly thick and fairly heavy. There's a movement towards thinner and thinner TVs. They want to go to glass. But basically, these diffusers have a bunch of little dimples in them, and these dimples reflect the light coming from the LEDs, which shine down into them, okay? These are all made with CO2 lasers today, but CO2 lasers in glass tend to crack the glass. With the CO laser, because again, the penetration is more controlled, we're able to drill very small holes. This is 33 micron diameter holes, and we're able to control the depth of the holes. So shown here are different sequential holes drilled with 1, 2, 3, 4, 5, and then 6 is finally a through hole in a 50 micron piece of glass. So very controlled, very stable holes. You can see there's no microcracking. It's very difficult to do if not impossible to do with CO2 lasers. The next application that's near and dear to our heart anyway is via drilling, okay? Via drilling today is done, the majority of via drilling, laser microvia drilling done today is done with CO2 lasers. And again, I mentioned before, CO2 lasers are diffraction limited to 55 microns and practically limited today to around 70 or 80 microns, okay? If you want to drill at an acceptable speed. So 70 to 80 microns are the holes that are being drilled today. Here we demonstrate holes that are drilled with the CO laser at 40 microns, okay? And I'll just take a minute to talk about the CO2 drilling process. It's a percussion drilling process in vias. And so typically a via is a hole that connects 2 layers in a multi-layer PCB board, okay? Both layers are, there's typically a copper layer, a dielectric layer, and you can see these here. There's a copper layer, dielectric layer, and another copper layer below. And for CO2 and CO, by the way, we coat the top with the copper oxide layer. First pulse goes through the copper oxide layer and then to some extent down into the dielectric. Second pulse, and it only takes 3 pulses for each hole, goes further down through the dielectric and may hit the next copper layer. Now the copper is 100% reflective at CO2 laser light, and by the way at CO, okay? And this is important for the application because then finally the cleanup pulse goes down, and even if you hit it with a lot of light, you'll never damage this layer below because it's 100% reflective. And CO laser has the exact same characteristics. The CO laser can be used for drilling this, and it can be drilled to drill much, much smaller holes. It can be used to drill much smaller holes. And if you want to drill the standard today, 70 micron holes, what you'll do is you'll have a 2x increase in your depth of focus. And that allows you to get a larger scanning field, which allows you to scan much faster. The final application I just want to point out has to do not necessarily with the wavelength or the material interaction, but the fluence that we can get out of the 5 micron laser. Polyethylene has always been a difficult material to process with lasers because of the spectroscopy. They're only CH stretches in the infrared for the most part. Those are shown here, and those are at 3.8 microns. There are no lasers that exist at 3.8 microns. So there's nothing to grab onto. CO2 lasers, you can see here, there's a small, tiny background amount of absorption, but not much. The same with the CO laser. But what you can do with the CO laser is you can focus the beam down very tightly, down to 40 microns, and that creates enough fluence to drive this process. It's very difficult to do with CO2 because you can't focus it as tightly. But again, you get 4x the power density or fluence with the CO laser over the CO2 laser, and that drives the process. And so you can see from this chart that we're able to process very thin, this is 20 micron thick, polyethylene at 3 meters per second. You're able to do the same thing with the CO2 laser if you really blast it with 140 watts, okay, but then you get a huge amount of haze and curl over. And then once you go to thicker polyethylene, for example, it's impossible to cut with the CO2 laser. It just destroys the material because you're trying to put so much power into the material, whereas with the CO laser, you focus it down tightly and drive the absorption in the material. So in summary, key performance attributes for this new technology, and again, this is brand new technology. Some of the laser themselves attribute is based on the highly reliable, field-tested hardware that it's borrowing from CO2 lasers. Okay, so it's brand new technology, and it's the first CO commercially available, but it's right out of the gate, piggybacks on all the reliability that we've had for 25 years in CO2. The 5 micron output really has about the same cost of ownership as a CO2 laser. So we've heard a lot about very expensive femtosecond ultrafast lasers that are doing processes that are pretty amazing, okay? But they also tend to have pretty amazing prices associated with them. These lasers will have only a slight premium over a CO2 laser, okay? And can do some pretty amazing things. Again, you have extreme power stability because of the multi-lines, immune to back reflection. Then as far as the applications go, you have stronger and weaker absorptions just because it's a new wavelength, 5 microns. The optical advantages are, like I said, tighter focus because it's 5 microns. You have higher power density, again, because you can focus more tightly. And if you keep the spot size the same compared to CO2, for example, you have twice the depth of focus. So in closing, I just want to say, we are introducing this laser to the market. There are demos available, and there are also these lasers set up at 5 of our different, we have a number of different application sites, but the ones you see there in the red already have 5 micron lasers or CO lasers set up in the laboratory. So if you have a material that you want to bring to Coherent, we can process that material with this new technology at any of those 5 different sites. So I want to thank you for your attention, and if there are any other questions you might think about later on the plane, please contact me.